Turning out today. This is your opportunity to ask me any questions you want about the Big Bang. So even you guys, you can ask. Yeah, we still need to focus this way. Can you focus out a little bit?
I don't think that can be focused to video.
Yeah, really? Let's see if the next one looks that bad. Yeah, that's pretty bad. There's only one camera, right? Okay, so we'll see what you can do, and we'll get started. So, okay, so hello. So today we are talking all about the Big Bang. So let's start off with an introduction to cosmology. So cosmology is the scientific study of the history and the evolution of the universe. So this is looking at what the history of the universe has been and where we're going in the future. So cosmology is a really interesting topic. It draws on almost every field of physics that there is. So every field that you have studied so far plays a role in our understanding of the history of the universe and where we're going. So this, of course, has been a question about where the universe comes from and where we're going. The origins of the universe have been questions that humankind have been asking for thousands, if not tens of thousands of years, but it's only been a real science in the last 100 years because we've only had the physical understanding and the tools to actually really make measurements and understand the contents of the universe enough to actually treat this as a science for the last 100 years. Okay? So now given that science is often frustrating to people who aren't scientists because there are only, you find that funny, because we can't answer all questions. There's only a limited number of questions we can answer. So we can answer, what happened in the past, and we can answer where we're going in the future. We can ask questions like, what is the universe made of, and how is it evolving? But there are questions that we can't answer. They are fundamentally outside the realm of science. For example, why we are here is a question that if any physicist tries to answer that for you, run. That is not a question that a physicist can answer, okay? So that is not a physics answer they're giving you. That is their personal answer that they're giving you. Okay? Another question that I get asked most common, this is the number one question I get asked about the Big Bang, is what happened before the Big Bang? And I'll tell you now, that is a completely irrelevant question for physicists. So the Big Bang created space, and it created time. And according to our physics understanding, that's a question that we can't answer, because there was no time before the Big Bang. Time was created in the Big Bang. So if somebody starts answering the question of what happened before the Big Bang, question them. Seriously, yes?
When you say time is created, what do you mean?
I mean, time was created. Time is part of the universe. So there's space and time. We'll talk about general relativity. And general relativity tells us about how space and time interact with matter. But those are parts of the universe that did not create outside the universe. So when the universe was created, what was actually created was the space and the time itself.
What's the thing before the space?
See, that's the question I can't answer. What's the thing before the space? That has a meaningless answer in physics, because time was created when the Big Bang occurred. So asking me what happened before the Big Bang is a question I cannot answer.
Isn't it self-contradictory? You need a space to have matter, but you have matter before space.
So the question is if that's contradictory, that we needed space to have matter and we needed matter to have space. That's a really great question. So let's see. Let's come back to that. So, but just going into that, realize, exactly like you have realized, there are questions that people want answered that are not necessarily questions that we can answer in physics. Okay? So when we're studying the universe, we actually have a really nice tool, which is due to the fact that light travels at a finite speed. We know that the speed of light is 300,000 kilometers per second. That means that light takes a finite time to reach us, which means as we're looking further and further out in the universe, we're looking at objects or things that happen further and further in the past. Okay, so we have a time machine, a cosmic time machine, which is just the light coming to us from distant objects, which lets us look back in time and actually get a picture of what the universe looked like billions of years ago, directly from the light coming from distant objects. Now, that's the one caveat to that is that's not looking back at our Earth, of course, billions of years ago. We're looking at other galaxies and stars that are far, far away that were billions of years ago. So there's a big assumption we make there, which we're going to talk about, which is that the universe way out there is pretty similar to the universe here, right? And that by studying what happened far away, we actually get a good understanding of what happened in our nearby universe as well. And that is actually a pretty major assumption that we make when we're studying cosmology. It's called the cosmological principle, and we're going to discuss that a little bit more as well. Okay, so to start this, we need to talk a little bit about general relativity. So this was Einstein's second theory of relativity. The first one, special relativity, we already studied, which dealt with the motion of objects. General relativity was his theory of gravity, which replaced Newton's theory of gravity. And the basic part of the theory that we need to get our head around is the idea that gravity is due to masses distorting the very space that they are sitting in. So you see this diagram here. This is really unfortunate how blurry this is, Wei. Maybe, Wei, can you call your manager and find out if there's something we can do about this? Uh-huh.
I think it was here for a second. Then I got
Oh, it was.
Oh, yeah.
Oh.
It's looking very clear on the webcast.
Oh, okay, that's good. That's good to know. Okay, thank you.
I'll let you know as soon as possible.
Okay, great. Okay, so you can see the image here of the fuzzy Earth distorting the very space around it. Right? So, and that is Einstein's theory of gravity in a nutshell. And this is not very intuitive, but the idea is that space, we sort of think of space as being nothing. Right? General relativity tells us space is something. It's an actual physical property of the universe, and it's one that can change. It's a physical property that can be stretched and distorted, okay, and it's stretched and distorted by matter. Matter in the universe actually changes the shape of the space of the universe itself. Okay. Space is something we usually take a little bit for granted as not an actual physical property. Okay. We think of it as being nothing. So that is not what general relativity tells us. General relativity tells us that space is an actual physical property. Okay. So, so there's this very famous quote about general relativity from John Wheeler, who's a physicist. It says, "Matter tells space how to curve, and space tells matter how to move." Okay? And that is the basis of general relativity in a nutshell, that matter distorts the space and time in its vicinity, and then how other matter moves through that space will depend on how it's distorted. So the fact that, for example, if I drop a ball here on Earth, Einstein tells us that it's falling because the Earth has distorted the space and time around it that is forcing that ball down to fall. Okay. So, so the key part of general relativity that we need to really get our heads around to understand the Big Bang is that space and time are actual real physical quantities, and they can be changed. They can be manipulated by matter in the universe. Yes?
I see vicinity, but gravity is a force that's not limited by distance.
That's absolutely true. So his point is that gravity is not a local force. It's a long-distance force, right? But of course it's much stronger when you're closer to an object than it is further away, right? So the distortion of space and time around an object will be much stronger the closer you are to that object.
Well, matter actually changed the entire universe because
Little bit. Yep, matter to the extent of matter is infinite. So, yep, yep.
So special.
You are special. You are a mass in this universe. You are distorting space and time. You should feel special. That's good. Okay, so general relativity. So general relativity tells us how space and time can be distorted by matter that's present. Okay? So one of the first things that Einstein did and other scientists did when they had this new theory of space and time was to think about all of space and time. And all of space, all of time is our definition of the universe. So when we're talking about the universe expanding and the Big Bang, we need to be thinking about the universe as being the space that we all exist in, okay, and the time through which we are evolving. Okay. Those are not just things that the universe exists in, those are the universe. The universe is the space that we live in and is the time that we are evolving through. Okay. So we'll come back to this again and again, but this is why this question about what happened before the Big Bang just doesn't make any sense from the physics standpoint, because time is part of the universe that was created when the universe was created. Okay. So, and the same with space. So when we talk about Big Bang, we don't talk about explosion out in space somewhere, because space did not exist. Okay. Space was created in the actual explosion itself, okay, and it follows the rules of general relativity. Space is an actual physical property. It's a property of our universe. Time is a property of the universe. As far as we can tell, they obey Einstein's law of general relativity in terms of how they evolve.
Was law of physics like established during the Big Bang or after the Big Bang?
So his question is, the law of physics established during the Big Bang or after the Big Bang? During the Big Bang, as far as we can tell.
So this thing is momentum conserved by the explosion.
So is momentum conserved by explosion? Absolutely. So in a sense, we will come back to this. The explosion itself, we need to get in a little bit more detail before we start asking questions like that. So it's a good question. Okay, so general relativity gives us the tool to ask how the space and time that we define as being the universe evolves. Okay? But general relativity also tells us that how it evolves will depend on what it's filled with, the matter, because we know that matter affects space and affects time. It distorts space and distorts time. So how the universe evolves will depend very sensitively on what is filling it, so the matter that's filling it. Okay? So if we want to proceed to create a model of the universe, to talk about how the universe evolved in the past and where it's going in the future, we need to understand something about what's filling the universe. What are the contents of the universe? What's the matter in the universe? And to proceed, so when they originally started doing this, they made a really presumptive assumption, amazing assumption, that amazing in the sense that it's so presumptive it's hard to believe somebody could make this assumption, but the assumption that they made is called the cosmological principle. And today, some of the active areas of cosmology are trying to prove whether this principle is true or not, and we'll talk about that a little bit. But the cosmological principle is basically the opposite of Aristotle's view of the universe. And the cosmological principle basically says that the universe is the same everywhere, so there are no unique positions in the universe. So us being here on Earth, the universe looks the same to us as if we were, billions of years away on another planet or around a different star in a different galaxy. And that is, of course, not true on a very small scale. Okay? I'm pretty sure that there is not another lecture room like this on Mars, for example. Okay? But we're talking here about on averages on big scale, so that matter behaves the same in our vicinity as it does in other parts of the universe, that the densities are roughly the same on average, that the laws that govern creation of solar systems and planets, stars, galaxies, that those are all about the same everywhere in the universe. Okay? So that is the cosmological principle, and it's an assumption that we actually have to make in order to proceed with understanding models of the universe, or creating basic models of the universe. And this is sort of the opposite of the Aristotle's view, right? That the Earth was the center of the universe and everything was revolving around us and we are special locations. So this is the extreme opposite of that, saying that we have no special place in the universe, that we are just, one of billions and billions of locations that all are basically the same. And that is an assumption that goes into initially creating models of cosmology, but it's also one that a lot of astronomers especially are trying to prove. So this is kind of hard to see. You'll see it better on the webcast if you want to look. This is actually a diagram that shows measured positions of galaxies looking out. And the goal of observations like this is try to understand whether things are sort of randomly distributed in the universe or whether there's a lot of structure. Okay, are there unique positions? And you can see that depends a little bit on your interpretation. If you look at sort of a squint, here we get to squint naturally. And sure, if you look, this is us here on Earth looking out in different directions, and these are all not even individual galaxies, but clusters of galaxies, many galaxies that are clustered together. You can see sort of in the big scale that things look roughly the same. You can see this side looks kind of like that side in terms of the number of galaxies and their distributions. But on the other hand, there also is a lot of structure in there, right? You can see areas where there are lots and lots of galaxies. So if you were on a planet sitting in the middle of in that point of space, then the sky would be a lot brighter at night. There'd be a lot of galaxies, a lot more stars, and it would look very different from on Earth. So there are also places like here and up here, which are giant voids in space where there are not many galaxies at all. So if you happen to be on one of the random galaxies that were located in one of those areas, your night sky would be a lot darker. So there wouldn't be many galaxies at all in your vicinity. You'd feel a lot lonelier. So there are certainly major variations throughout the universe, right? So when we're talking about cosmology, we were talking about, not regions on this skies, but the universe as a whole. So that still seems to hold true, that the cosmological principle is true on the big scales, okay? But certainly not on the local scales. There is a lot of structure in the universe at all different size scales, down from, up from major clusters of galaxies like these bright spots here, of course down to solar systems and planets, the very tiny scales. Okay, so when Einstein created his theory of general relativity, he and others immediately started thinking on the big scale, the cosmological scale. How was the universe as a whole evolving, or was it evolving? And when Einstein applied his theory of general relativity to the universe as a whole, as opposed to just a sun or a solar system or a planet, he found a really surprising result, or at least a result to him that was so surprising he couldn't believe it was true. So his result that he found was that the universe could not be static, meaning that it couldn't be just a distribution of mass that was staying still. So what Einstein saw in his theory of general relativity was that the universe had to be expanding or contracting. It couldn't just be a static universe. So that meant that his theory was predicting that the universe had to be evolving, that it wasn't sitting still in time. It either had to be expanding, so the distance of separation of things was getting bigger and bigger, or it had to be contracting, so things had to be coming together in a big crunch. In hindsight, that's not so surprising. The universe we know that general relativity tells us that space is affected by matter. Matter is undergoing gravitational attraction, which is attracting, so every galaxy is attracting its neighbors over a very large distance. And so the fact that that you can have all these stars and galaxies sitting out there and they're not gravitationally attracting each other and shrinking down isn't so surprising in hindsight. Okay. But that went completely against Einstein's view of the universe. So the great Einstein, actually, who came so far in terms of changing our view of the universe, couldn't change his own view that the universe could not be evolving, that it had to be a static place that existed infinitely in time. So Einstein did something which he called later his biggest blunder, which was that he fudged his theory of relativity in order to create a model of the universe that was static. So he added a repulsive force, so gravitational attraction is, of course, a collapsing force. And he added something called the cosmological constant, which is completely a little fudge factor in general relativity that provide a repulsive force to counter the force of gravity. And so Einstein built that into general relativity because he didn't like a view of the universe that was evolving with time. He wanted to see that general relativity predicted a nice static universe. Now, I'm not saying that he did anything wrong there. That's absolutely not the case. It's certainly something that could exist in his theory, but it's something that he had to add. He had no evidence that that was true or a factor, but that he built that into his theory in order to overcome that bias that he had that the universe couldn't be evolving. So the cosmological constant, we'll come back to that in a minute. It was a factor that Einstein built into general relativity in order to create this idea of a static universe, one that's not changing in time. Okay? But there was another physicist called Friedman. He was actually a physicist and a mathematician who also looked at these models. And Friedman showed that Einstein's little fudge factor didn't work, that you could add it, but it didn't actually create a nice, stable, static universe, that it was an unstable configuration. So the universe couldn't stay stable and flat with time. It still had to be evolving, even if you included this little fudge factor that Einstein put in his theory. And so Friedman refuted Einstein's idea of a static universe in general relativity and basically evolved the original theory of the Big Bang, even though he didn't call that. He basically proposed that the universe had to be expanding, that from the laws of general relativity that there is not possible to have a static universe that wasn't changing in time. So that is the origin of the Big Bang theory. And basically at this point it was predicting that the universe had to be expanding through space. So now the question is, what is expanding? This gives me my chance to play my favorite movie clip of all time from Annie Hall. Who's Annie Hall? Annie Hall is a great Woody Allen movie. Okay, can we turn the sound back on, Wei? Okay. We're having a very casual lecture today. I hear the whistle, so okay, let's put up with that for just a second.
And it's funny, I'm not a morose type. I'm not a depressive character. You know, I was a reasonably happy kid, I guess. I was brought up in Brooklyn during World War II.
He's been depressed. All of a sudden, he can't do anything.
Why are you depressed, Alvy?
Tell Dr. Flicker. It's something he read.
Something you read, huh?
The universe is expanding.
The universe is expanding?
Well, the universe is everything. And if it's expanding, someday it will break apart, and that will be the end of everything.
What is that your business? He stopped doing his homework.
What's the point?
What has the universe got to do with it? You're here in Brooklyn. Brooklyn is not expanding.
It won't be expanding for billions of years yet, Alvy. And we've got to try and enjoy ourselves while we're here, huh?
Great philosophy of life. Enjoy yourselves while you're here. Okay, so Alvy's mom in that movie was absolutely correct. Brooklyn is not expanding. So let's ask, in the Big Bang Theory, what is expanding? So the Big Bang Theory tells us that space is expanding. So space itself is expanding. So that is the structure of the universe that we are all embedded in. Okay? So that also tells us that, for a little bit of complicated reason that I'll talk about in a second, that photons are expanding. So light particles in our universe are slowly expanding as well. Okay? But the Big Bang Theory does not tell us that objects are expanding. In fact, quite the opposite. So, and that's because the size scale of an object is set by the local forces. So the balance between electromagnetic forces and gravitational forces on the small scale. Okay? And we're talking about general relativity and the Big Bang. We're talking about very tiny forces over very long scales. So the fact that the universe is expanding and space is expanding does not mean that the Earth is expanding, or that you are expanding, or even that our galaxy is expanding, or even that our group of local galaxies is expanding. Okay? It only means that space is expanding on the very large scales, and that things that are very far apart from each other are expanding relative to each other. Okay? I mean, their distance between them is expanding, okay? But the objects themselves are not expanding. So you are not expanding, and Brooklyn is not expanding. So, but it's still your business, because it's interesting to know. Okay, so when you're thinking about the expansion, you should be thinking about space on the very largest scales, okay? Not about individual galaxies, not about the solar system, not about stars, not about planets. So these things have their size set by the laws of physics on the very local scale. So it's only on the biggest scale, the space between very distant galaxies, that the universe is expanding. Okay, so let's talk about this prediction. So the prediction from general relativity that the universe is expanding. And we've had three primary tests of this theory, which has convinced most physicists that this is a correct prediction. Okay? And so let's talk about those three tests and why they provide such conclusive proof that this theory of the Big Bang expansion is correct. So the first test comes from Hubble expansion. So that's named after Edwin Hubble, who was an American astronomer, who in the late 20s was looking at the distance to local galaxies in our nearby neighborhood, and was looking at their velocities and how they were moving. Okay? He was aware, of course, of the predictions of general relativity and Big Bang. And he found a surprising result, okay? Or a somewhat surprising result. Remember, at this time, general relativity was not widely understood. It's kind of a complicated theory. And the implications of Einstein's and then Friedman's predictions that the universe could not be a static place weren't widely even known, much less, something people were thinking about. So it was sort of a novel part of that theoretical structure. But Hubble was an astronomer, and he was actually looking to test this theory, and he found what was a surprising result at the time turned out to be the first proof that, or the first conclusive evidence that the Big Bang actually had occurred, and that was the fact that when he was looking at galaxies, they all appeared to be speeding away from us. Okay? So, and the further we look out in space at galaxies, the faster they appear to be receding from us, moving away from us. Okay? So that means everything in the universe looks like it is expanding away from us here on Earth, or us in the galaxy. Okay? So you might ask a question. I wouldn't take it personally. Why is the universe fleeing away from us? Okay? And the answer is it's not just fleeing away from us, it's expanding. And that's the same everywhere in the universe. So it appears true everywhere that you look. So here's a little diagram that tries to show that. So imagine that we are sitting here on this little pink galaxy, okay, and here are all the other galaxies surrounding us. And you can think of those galaxies, one thing way people think about the universe expanding as points on a balloon. Okay? And as the balloon expands, those points move away from each other. Okay? So you can think of the balloon as being space itself, and all the points as being individual galaxies. And as that balloon expands, those individual points all move away from each other because the space itself, the surface of the balloon, is expanding. Okay, so if you imagine that we're sitting here on this little pink galaxy, and we're looking at all the other galaxies around us, then if we let the universe evolve a little bit in time, okay, as that space expands, all the galaxies move apart from each other. Okay, so we would see every single one of these galaxies moving away from us. Okay. The further away they are, the faster they appear to be moving. Okay. But the same is true if you're in any of the other galaxies. So, for example, if we were sitting in the blue galaxy, okay, we would see every other galaxy moving away from us. Okay. And the same is true from every point in the universe. Okay. So this goes back to the cosmological principle that we're not at a unique position in the universe, that every point is roughly the same as the others. And the fact that we see everything moving away from us is a sign that the universe as a whole is expanding. And the same is true if you're at any other position in the universe. Okay, so this is a pretty big clue that the universe is expanding. So there are other ways people tried to explain this away, but the expansion is by far the easiest way to understand the fact that everything appears to be receding away from our position here in our galaxy. Okay, so Hubble expansion, that was the first real clue that the universe was expanding. And it was at this point when Hubble made the announcement of those findings that Einstein came back and said that adding that cosmological constant to general relativity, his little fudge factor, was the biggest blunder that he had ever made in his career. So he would have definitively had predicted that the universe was expanding if he had not went back and fudged his theory of general relativity. So Einstein regretted adding that little fudge factor, but it comes back. We're going to talk about that again in a second. So he actually should embrace that little fudge factor because it turns out to be actually a very crucial part of Big Bang. Okay, so the second test. So the second test we have of the Big Bang comes from the creation of the light elements. Okay. So you can think about this running the universe backwards. So if we run backwards in time, right, we have all the galaxies and the stars, and they all collapse down into a hot soup of stuff. Okay? And as it collapses further and further, it has to get hotter and hotter. Okay? So the explosion is running that backwards in time when things are expanding out. Okay? But if we think about it, as we go back in time, it means that things had to get hotter and hotter, or back in the early universe, back in the Big Bang. Okay? And if we keep extending it down to earlier and earlier times, so earlier in the Big Bang, then we know that the elements couldn't exist. So helium, carbon, sulfur, silicon, it was too hot an environment in the early universe for those to exist. So what did exist were the individual protons and neutrons that were later became part of the elements. Okay? So the theory is that early in the Big Bang, we just had the particles themselves, the protons and the neutrons. And as the universe expanded and those cooled, then they could collide and start forming heavier elements. Okay? So we could get, the idea is we have early on a very hot soup of neutrons and protons that are all flying around and interacting with each other. Okay? And they're colliding, and as the universe expands and cools off, then those can start forming into heavier nuclei. So, so we can get neutrons combining with protons, and maybe that would combine with another pair and form helium. Okay, so we can create heavier elements out of those original particles that had to exist by themselves in the early universe. Okay. Now, there are two limits to that process, though. One is just that the universe is expanding, so it's cooling. Okay, so remember that protons and protons want to repel each other. So the only way they can get close enough to actually form a nucleus is if they have a lot of energy. So they have to be really hot. So as the universe expands and cools, this process is going to get cut off by the fact that the protons aren't hot enough to get close to each other anymore. Okay. And the second limit is, remember that neutrons are unstable. They decay with a half-life of about 10 minutes. So, you know, after a few hours after the Big Bang, there weren't any neutrons around, or there weren't many neutrons around, free neutrons around, to create heavier elements. So much less that the fact that they've cooled dramatically, and so so they wouldn't have enough energy to form their reactions anyway. But there are two limiting processes to how long this creation of heavier elements could have occurred in the Big Bang. Okay, so in 1948, a physicist named George Gamow proposed that perhaps all the elements we see in the universe around us were created in the Big Bang, and we could use this as maybe a test of the Big Bang theory, if we could use the Big Bang theory to predict the number of elements, how much carbon there is, how much nitrogen, how much oxygen there is. And he was amazingly wrong. So this was a very bad proposal, but it led to a really major discovery, which was one of the major tests of the creation of the creation of the elements. It's one of the tests of the Big Bang. Okay? So, and that is that. So if you do this process, if you do this theory, and you follow the evolution of the neutrons and protons, and what's created, what it actually predicts is that the universe in the Big Bang itself, nothing that was made that was particularly heavy. So carbon, oxygen, nitrogen were not formed in the Big Bang. There just was not enough time for these to interact to create heavier nuclei. Okay? But what was created, or could have been created, was helium and lithium and very light elements. Okay? And so, so when Gamow and his collaborators applied this theory, this nuclear physics, to the early universe, they basically didn't predict that you would see a universe that looks like we see around us with all the heavy elements, okay, that we're all made of, but that we just see a universe composed of hydrogen, 25% helium, and a very little bit amount of lithium. So that sounds like it might be a bad theory, but the astronomers come along, okay? And I'll remember, if we look back in time, right? If we're looking at things far away, we're looking further and further back in time. And when astronomers look farther away at what we call more pristine objects, or older objects in the universe, they see exactly what this theory predicts, that the universe was composed in early times of mostly hydrogen, a little bit of helium, and traces amounts of lithium. Yes? On this plot itself. So this is a plot of, this is really, okay, that's a little bit better. So this is a plot of, this is completely a theory plot. So this is a plot of how much of these elements are created versus how much matter there was in the early universe. So the overall, what we call the density of the early universe. So this is actually not a plot of a single prediction, but many, many predictions. Okay? And the question is, if we don't know what the density was of the universe, then we can at least predict what the abundance is for all the different densities. Okay? So now this gray line here in the middle is our best measurement of what that density actually was. what that density actually is. And this turns out to be the density actually of normal matter, of baryonic matter that matters in here. And so, so by combining this theory, which is the predictions for all different densities, versus this gray line, which is the prediction for what our best guess is what the density of baryonic matter is in the universe, then we should say that the number, the elemental abundance we should measure should be the points right along this line here, which is exactly what we see when we look out in the universe. So this is a range of predictions, and this is the best fit, and that means there's a very specific ratio of helium to helium-3 to lithium to deuterium, and that's exactly what we see looking out in the early universe. Yeah?
Curious about how the universe cools down.
You're curious about how the universe cools down.
Consistent with the law of entropy, and I think the binding energy of elements will increase the temperature.
So the question is it consistent with the law of entropy? That's a very deep question. Absolutely. So entropy is only increasing in the universe as we go along. So, but let's come back to that towards the end, so because we could easily get distracted on entropy questions for a long time. So, but short answer is entropy is always increasing in the universe. Absolutely. So, on the big scale. So it's absolutely consistent with that. So, is there another question over here? Okay, so let me just recap this shortly, which is that so the theory predicted what the composition of matter should have looked like back in the early universe, and when we look back, when the astronomers look back, they see exactly the composition that was predicted, the ratio of hydrogen and helium to lithium that is consistent with the Big Bang. So this is taken as a second test of the Big Bang theory, which was proven by observation. So now the heavier elements, so the stuff we're made of, carbon, oxygen, nitrogen, silicon, aluminum, everything heavier than those very light elements, we now believe was produced in stars and in supernova explosions that followed after. So this comes from structure that happened later in the universe as it evolved. So that means we are all nuclear waste, if you want to think of it that way. Okay, so the third test of the Big Bang. So this was the third, and for many people, sort of the definitive proof that the Big Bang theory was correct. So this model we just discussed of the Big Bang nucleosynthesis. So that's how light elements were produced in the early universe. So it made an additional prediction. So the idea was that the universe, of course, was much hotter early on, and as it cooled, then as all the stuff cooled, then there wasn't just matter in the universe, but there was radiation. So we've already talked about thermal radiation a lot in this class. Stuff that's hot emits light. It emits light at radiation at wavelengths that is characteristic of the temperature of the objects. So when we're talking about the early universe being filled with neutrons and protons, being very hot, it was also filled with radiation, okay, thermal radiation. So so the idea was that thermal radiation that was around in the Big Bang basically would cool, just like the matter cools when it expands. And there's a reason that we think that was decoupled from matter at about 300,000 years. So about 300,000 years after the Big Bang is when all these nuclei that were formed. So we had nuclei that were formed in the explosion itself, but they were still too hot to get electrons, so to form atoms. Okay? And about 300,000 years after the Big Bang is when it would have cooled enough that electrons could form. And so we'd actually have real atoms that formed, not just heavy nuclei. And at this point, the radiation basically became free. The universe became transparent, and all that thermal radiation was free to travel independent of the matter. So this is kind of like I have an analogy here looking at the surface of the sun. So we can see the surface of the sun from the thermal radiation that's coming from below, but we can't see beneath the surface of the sun. Okay? So we're seeing the light as it's freed from the sun, so that last surface where the light is free to escape. So the idea is that if we look back in the universe, we should see that as well. We should see this point when thermal radiation could escape from the matter in the early universe as it was expanding. And this was a prediction of the Big Bang Theory, but it was actually one that was actually discovered surreptitiously in 1964 by, in fact, two engineers, Arno Penzias and Robert Wilson, who were working for NASA. So this is a famous discovery. They had this is a big radio telescope. It's actually, so it's a microwave. So microwaves are a part of the radio band. So they're longer wavelengths than infrared. And this was a telescope, or just they call it an antenna, but it's basically a radio telescope that was designed to track satellites for NASA in the early 60s. And these guys, Penzias and Wilson, were basically testing this telescope and trying to calibrate it, and they just kept picking up noise. They just thought it was junk. In fact, they thought the story goes, they thought there were birds nesting in the telescope that was creating a lot of noise. Okay? And so they did everything they could to try to isolate this and get rid of it, and they couldn't. And this was a site that was close to Princeton, and so they actually turned out to be, one of them was friends with some physicists at Princeton, and these were physicists who were actually just starting a project to try to detect this relic radiation from the universe. And they went and talked to them about what they were seeing, and they were like, oh, you guys just saw what we were trying to discover. And so they discovered this background radiation filling the universe. So this is thermal radiation. We call it the cosmic microwave background. It would have started off when about 300,000 years after the Big Bang at a temperature of about 300,000 Kelvin. So that's about half the temperature of the sun. So this was when the universe was still expanding. It was still very, very hot. And you can literally think of this as like the light coming from the surface of that, all the matter before it ever collapsed down into a star, but when it was so hot, like the surface of the sun, right? And then at that point, it became free of the matter because all the electrons joined into atoms. It was free to travel, and then as the universe expanded, the light cooled. Okay? And as it cooled, the radiation cooled, it went to longer wavelengths. So it went from 3,000 Kelvin, and then it cooled down to what we measure today, which is about a factor of 1,000 lower, so just about 3 Kelvin. And the Big Bang, so that theory of creation of light elements was predicting that there should be radiation somewhere in the order of a few Kelvin. So they didn't predict an exact temperature, they sort of predicted a range. And that's exactly what we see. And this is a measured spectrum from COBE satellite, which was partly built here at Berkeley. And this is a black body spectrum, and it's the most perfect black body spectrum that's ever been measured. It's amazingly precise observation of a perfect black body, perfect thermal spectrum, 2.7 Kelvin. So that's just filling the entire universe, and it was direct prediction and evidence of the Big Bang theory. So this is a detailed plot which you can't even begin to read, but this will be in the notes. So all these notes are going to go up on the website today. So this is just a timeline of the Big Bang, which talks about some of the things that we already discussed. So, but the key points we've talked about today was around 3 minutes after the Big Bang is when creation of the elements began. Okay. So that's when the light elements, helium and lithium, were created. It would have expanded for about 300,000 years before the cosmic microwave background was basically released free to the expanding universe. And then, in our current understanding, the universe expanded for another million years or so before matter started collapsing down to form stars and galaxies and all the stuff we actually see in the universe around us today. Okay, so we know that when we look out that the universe is expanding, okay, but we really want to know how long has it been expanding, where is it, what was its history like, and where is it going in the future. So this is a plot that you guys may have seen before, maybe didn't understand. This is a plot of the relative sizes of the universe, so that's relative today. So 1 on this scale is basically how big things are today. And so here is 1, that's the size of things today, and here is now. Okay? And we know that the universe is expanding, so we know that if we look towards the future, things are getting bigger, and if we look towards the past, things are getting smaller, space is getting smaller. Okay? But we want to know more than that, of course. We want to know, of course, if things were getting smaller at the past, that means they started down at some time at a point, and how long ago was that? And of course, if things are getting bigger now, it doesn't mean they'll necessarily always get bigger. Okay? And one of the questions that drives cosmologists is the universe always expanding? Is it going to expand faster, or is it going to turn around and start collapsing back down, okay, so that the universe will shrink? And these are all things that can happen according to general relativity. And whether they happen or not depends on what the universe is actually composed of, what the matter is. So the question is, if it collapses down again, is it possible to have another Big Bang? Maybe. That's a really good question. So I don't want to say anything that's really bad. I mean, stupid bad. Yeah, I think it depends on what theory you're looking at as well. So certainly you have a lot of energy there, so that could potentially go into another explosion. So, but you're basically ending time. So could it go into creating a new universe? That's a really good question. So there have been theories that predicted this sort of cyclic expansion and collapse of our universe. So, but we don't have to worry about that because that's not what's happening. So it's a theoretical question. So. Okay, so one thing we know from our current observation is that the universe is 13.7 billion years old. And I put a wow there because that's amazing that we can declare definitively today how old the universe is to 3 significant digits. So this is a question that, of course, has been at the top of humankind's thoughts for thousands of years, and we have an answer today, which is 13.7 billion years. That is the age of the universe. Okay. We can ask how it will expand or in the future, whether it collapse, and that of course depends on the contents of the universe, how much matter there is that's trying to slow down this expansion. And so we need a better understanding of what's in the universe if we want to understand how it's evolving in the future, not just where we came from in the past. Okay. So a lot of cosmologists today are looking at that question not just of where we come from, but where are we going in the future. And to understand that, we really need to understand better what is the composition of the universe, how much matter is there, and is there other stuff in the universe. Okay. So I'm going to talk about a few observations that are pointing in that direction, especially ones that are important here for Berkeley. So the first one is the mapping of the cosmic microwave background. So this background is, we know, thermal radiation. It's filling the entire universe. And this is a image. This is a picture of the universe in that microwave thermal radiation. So that is a picture of the entire universe, okay, at 3 degrees Kelvin. And you can see there's a lot of structure in that. There's a lot of peaks and valleys in there, and that's the structure of matter on very large scales. Okay? At the time when this radiation was still interacting with matter, which was 300,000 years after the Big Bang. So these bumps and wiggles, they look very significant on this map, but that's because they've been blown up. Remember that black body is almost the most perfect black body we've ever measured. So it's very uniform on the sky. Okay? The scale of these little bumps and valleys is about 1 part in a million. So they've taken what is a very uniform background covering the sky with cosmic thermal radiation, and they've blown it up just to show the little tiny bumps and wiggles on top of it. So, but these little tiny bumps and wiggles are telling us about how matter was distributed, how all the stuff in the universe was distributed 300,000 years after the explosion. Okay? Now, how the matter gets clumped up like this depends on how strong gravity is acting, because the matter gets clumped because it's being gravitationally attracted to each other. So this is giving us a very good measurement of the structure of gravity 300,000 years after the Big Bang, which depends on how much matter there was in the universe, how it was clumping. So by imaging the cosmic microwave background, this thermal radiation, what they're trying to do is literally measure how matter was gravitationally collapsing back in the early universe. And so this was the first map of the radiation, and this one, George Smoot, professor at Berkeley, the Nobel Prize in 2006, which he shared with one of his colleagues for producing this first image that basically gave us some of the first evidence, direct evidence of what the universe is composed of. And we're going to talk about that more in 1 second. This is the current map, so this has been updated. So this is a map from the early 90s from a NASA satellite called COBE, which is built in part here at Berkeley. And this is the best image we have currently from a satellite called WMAP. And so this is a NASA image. And you can see, you can split back and forth between these. This is a much higher resolution image, so you're getting the structure in smaller and smaller scales. Okay. Oops, went forward too one. Okay, these are the same image. This one is just a lot blurrier. Use a lower resolution camera than this one. Okay. So this is allowing us to measure the structure at smaller and smaller scales, which gives us a much better model for what the composition of the universe is. Okay. The second observation I want to talk about before I tie these together is that Hubble's expansion. So at the beginning we were talking about how Hubble was measuring the distance to galaxies and how fast they were receding from us, so he could tell from that the universe was expanding. It was the first direct evidence we had of the Big Bang. So Saul Perlmutter, who is a professor here in physics, and a number of his colleagues, they won the Nobel Prize this year for taking those measurements and pushing them either further out into space. So they were doing these measurements of how fast is distant stuff receding from us. Okay. And what they found was completely a surprise, which was that not only is stuff not only is this Hubble's law hold that stuff that's further away from us is receding from us faster, okay, but they also found that it's not just got a fixed velocity, but that it's accelerating. There's actually something that is pushing the universe apart faster and faster. So not only is the universe undergone an explosion, but there's something that's actually making it accelerate faster. So it's speeding up, okay, which doesn't sound like a very conventional explosion at all. Okay, there's something in space that's actually repelling all the matter, okay, and making it accelerate faster. So these observations and ones by other cosmologists have given us a picture of what the universe is actually composed of, and it is a completely fascinating picture because we don't understand 95% of it. So And our current picture of the universe, by understanding from the measurement from the expansion, from the measurement of the structure in the cosmic microwave background, we know that the matter that we are familiar with in the world around us is only 5% of the stuff in the universe. So everything we know, everything we're familiar with, all the physics we've been talking about this entire semester only covers 5% of the stuff in the universe. So we know that 23%, okay, so 5 times what we know about of the universe is matter, but it's what we call dark matter. And we call it dark matter basically because we don't know anything about it. We know that it's mass. We know that it acts gravitationally, so it has a gravitational pull. Any mass has a gravitational pull, but it doesn't have any other interactions that we've talked about. It doesn't interact electromagnetically, so no photons, no light, no electrons interact with it, protons, nothing. It's a completely different type of matter than we are familiar with. And there are theories of particle physics that maybe predict this, but, I mean, they don't predict it, but they may or may not explain it. But they are all sort of not our standard models of particle physics. So we live in a funny universe. We are only familiar with 5% of the stuff in the universe. 23% of it is this dark matter. In some ways, dark matter at least is a little bit comforting to us because we know something about it. We know it acts gravitationally, and so we can sort of fit that into a little bit into conceptual physics. The fact that the universe is accelerating, which is the observation I just showed that Saul Perlmutter won the Nobel Prize for this year, means that Einstein's cosmological constant is back. So this little fudge factor that he put in his theories that was trying to balance gravitational pull, remember? So gravity would make the universe tend to shrink. Okay, so he added this repulsive force, this little fudge factor, which he called the cosmological constant, in his theory that was balancing that. So that is a repelling force. Okay? So the observations that we now have say not only is that there, but it's much stronger than Einstein ever predicted. It's not just balancing gravitational pull, it's actually making the universe accelerate outwards. So Einstein's still an evolving story, right? His biggest blunder was introducing this cosmological constant, which basically after Hubble found the expansion, people basically did away with because there was no need for having that in the theory of general relativity anymore. It's back because now we have direct evidence that it's really there, and it's not creating a static universe, though. It's actually creating an accelerating universe. We call this dark energy, and it's 72% of the composition of the universe. And this one we really have no idea. We have absolutely no idea what this is. So in some ways it's exciting times. We know that 95% of the universe we do not understand what it is at all, but at least we have the tools to, remember our first lecture on science. Big part of science is knowing what you don't know. Okay? We don't know what 95% of the universe is, but that's kind of exciting. It gives us directions to try to understand more. So, and maybe, I can't make any firm predictions, but my guess is we'll probably have a much better understanding of dark matter sometime over the next decade. There's a lot of work that's being done to try to actually measure this directly and what it would be. Dark energy, I don't know. We might never figure out what dark energy is. It's an enigma. So, but I don't know. There's a lot of smart people out there, so maybe we will figure that out sooner rather than later. Do you have a question?
What does the percentage be? Is it mass-wise or volume?
So you're asking what the percentage is. The percentage is really the fraction of the, we call it the density, but you really just think of the energy that's filling the universe. So it's only 5% of that is matter. Remember, E equals mc squared. The matter of the universe is energy that's filling the universe. And only 5% of that is stuff that we know. Are you buying that? Yeah. So you can think of it matter, but dark energy is probably not matter. It's really just energy. So here we're really talking about energy, the energy density of the universe. So, yep. Is there any, yeah. Was gravity created after the Big Bang? Great question. Was gravity created after the Big Bang? Wow, that's a really good question. Yes? Please do. Save me here.
I think maybe, at least from my perspective of coming from, a better way to think about the Big Bang rather than the creation of stuff is if you take the laws of physics and you run them backwards in time, you come to a point where everything would have been, where basically the equations break down. Because if you did, everything would have all been at a single point. So we really don't know what happened then. It's just we say there was a Big Bang where everything started. That's the only reasonable way to read what the equations are telling us. But they don't really tell us what happened there. They just tell us there was a point, so we don't understand it.
Yeah, that's a good point. Yeah, that's a good point.
Big Bang is extrapolation of physics.
Big Bang itself is the application of the physics that we know back as far as we can. So, so I will add something to this, which is we do know in some sense, well, we suspect that general relativity is wrong. And that's because general relativity and quantum mechanics, which we're going to talk about next Tuesday, are two fundamental theories of the universe that are completely inconsistent with each other. One of them is talking about matter on very small scales, quantum mechanics, and general relativity is talking about matter on very big scales, and when you have a lot of mass. Okay? And both of them work very well in their respective areas of the universe where they work. There are only two cases we know of where they come into direct confrontation with each other. One is black holes, which we haven't talked about, but it's where matter gets so dense and so collapsed that you have to take into account both theories at the same time. And the other is the Big Bang. So, so general relativity, there's a good chance that our theory of general relativity breaks down because we've never really tested it in those extreme regimes. String theory is it's a name you probably know, and hopefully we'll talk about that a little bit on Tuesday. String theory is trying to reconcile general relativity and quantum mechanics together into one theory. And this is exactly the realm where string theory works, where it's trying to work. And so I would say, to answer your question shortly, exactly like Nathan was saying, that gravity as we know it probably did not exist. But gravity in the form, some other form that is consistent with quantum mechanics certainly was the dominant force at that point. And so that's what makes it interesting to us, because it's a realm where we're looking at gravity in a completely different physical situation than we're used to it in the world around us. I don't know if that answered your question. So that borderlines on one of those questions we can't answer. So, but it is the things that keep physicists up at night. Exactly those type of questions. Okay, so that is our universe. Oh, and last thing I got here are a bunch of references. So this is going to get posted on our website. So let's just ask some more questions. There's got to be some more questions. You had questions about entropy. I know you've been asking about entropy all along. So, so we haven't talked much about entropy or any at all about entropy in this class, because it's kind of a subtle topic. But for those of you who studied it before, we have this basic law of physics that entropy is always increasing. So it's kind of tied with time, that the direction of time is the direction where entropy increases. So the Big Bang explosion, is your question whether entropy is still always increasing during that point? And the answer is yeah, absolutely. So one way we think about entropy is in terms of structure, that things that are very highly structured have lower entropy, and as they get more random and chaotic, they have a higher entropy. And so the universe tends to always move towards the regimes of higher entropy. And there are cases where we can create lower entropy at a local scale, but it's always at the cost of creating entropy overall. So the universe is sort of like the biggest example of that, because we went from this very condensed state where everything was really tightly packed and almost the most uniform state you can have to what today we have is an extremely chaotic universe around us. And so so absolutely the entropy is always consistent in this picture. So, yes?
Yes, the universe seals things as expanding or it's open.
So, okay, sorry, that's a really great question. So, the question is the universe still expanding or it's open? Well, now we think from these measurements that Saul Perlmutter and others won the Nobel Prize for, that there's different potential futures of the universe, and we think this is the one that we actually live on, where the universe not only will continue expanding, but it will continue expanding faster and faster. And so that is the limit of our knowledge, is that the universe will keep on expanding, and it will expand faster and faster as it goes on. So which is why we don't have this paradoxical question of, could it collapse back and form another universe? So, well, that's not the universe that we think we live in, at least currently. Yeah, great question. So the question is, what's beyond the extent of the universe? As far as we know, it's more universe. So in fact, we don't actually know whether the universe is infinite or not infinite. Right now, it looks like it is consistent with being infinite. But we do see, we have seen more and more of the universe as the universe expands. So just because, we have this concept called the horizon, which was how much of the universe could affect us by the fact that, light or anything takes a finite amount of time to reach us. So as the universe gets older and older, there's more time for information to travel across the universe, which means we can see further and further out. And so we have seen more and more of the universe over time as we've evolved over our 13.7 billion year lifetime. And we just keep seeing further and further out more and more stuff. So that's a really great question. So can we keep on seeing further and further out? But so far we've just seen more universe, more stuff that looks completely consistent with what the universe looks around us now. So could be that it's infinite. So there's this weird thing that it came to a point, but maybe it's infinite. So it boggles the mind to think about. So do you have something? Okay. Do you have a question? More questions? Yes?
I thought you said you don't really know much about Dark matter at all, but we can assume that it was like the point that you were describing with the other matter, right? Why is it that it reacted then but doesn't react with anything now?
So the question is about dark matter and how it reacts with other matter, and how it reacted back then and how it doesn't react now. So dark matter is interesting. So so these reactions here, right, between neutrons and protons back in the early universe are dominated by the forces we already know about, the electromagnetic force and the strong force. So that was dominating the interaction. So our thoughts are that, while this was going on, there were big, I just put them as big particles, we don't know what they are, but there were dark matter particles running around back there in the early universe. They just, the interactions that were going on at this earlier time were dominated by the electromagnetic force and the strong force. These only interacted gravitationally with the other particles, which was not of a dominant force back then. And so the fact that these were there didn't have any effect on what was happening with these other particles. So these were almost invisible to all the other particles in the area. So the dark matter was there, and it was, present. It didn't have any physical interactions with the other particles. So it was not affecting those reactions that were going on. Now, we do have very strong evidence for dark matter besides the cosmic microwave background. It's still gravitationally attracted. It still has a mass. And so that means when you're talking about scales where gravity really dominates, like galaxies and clusters of galaxies, so big scales in the universe, then the dark matter plays a really dominant role in the structure of galaxies. So for example, when we look out at some local galaxies, you often see these beautiful spiral structures in the galaxies. And we can see literally how, stars and well, not planets so much, but gas clouds, stuff in these galaxies are moving around, right? And we know the basic laws of gravity, how fast they should be moving, given how much stuff was there. And what we see is, the parts of the galaxies we can see is not the dominant mass. So this is sitting in some much bigger galaxy that is composed of these dark matter particles. So 5 times as much mass is dominated in this stuff that we can't see, so which completely dominates the structure of the galaxy. So it's dominating why the galaxy looks like it does, but that's just because the gravity of that bigger thing has dominated how the stuff is collapsed down into galaxies. So we have a lot of direct proof that dark matter exists, but all that proof comes from the fact that it has mass and it's got a gravitational pull. But that was not the dominant interaction early on, so basically dark matter was just sitting there, but it wasn't interacting with anything in the early universe. So, yes?
Is there some dark matter on Earth?
We don't know. That's a great question. Is there dark matter on Earth? Is the question, and probably. If it's a particle like this, then probably, but there are theories that maybe dark matter is are big black holes or primordial black holes or something really exotic like that. We don't know. We want to test that, so that's a good question. Yeah. Oh yeah. So the question is if there's evidence for dark matter beyond rotation curves of galaxies. And there's a lot of astrophysical evidence for dark matter. So first off, the CMB, the structure of the CMB is completely dominated by the dark matter. We see bending of light around big massive galaxies, which is much more mass than just composed of the stars and gas in the galaxies. So we know that it's dominated by the dark matter of the galaxies. And the structure of that could look completely different from the galaxy it's sitting in. So we in fact have evidence of some galaxies that have been knocked out of their dark matter halo. So we can see the dark matter halo from the gravitational interactions, which is completely separate from the galaxy itself. So there's a lot of direct evidence, astrophysical evidence. All comes from gravitational effects, because that's the only interaction that it has. Maybe the weak force, which we haven't really talked about, but that's such a small force that it doesn't dominate anything in large scales. So the question is, how would a galaxy get knocked out of its dark matter halo? Collisions. So galaxies collide all the time. In fact, our galaxy is on a collision course with Andromeda, our nearest galactic neighbor. So the dominant force, so your question is dominant force is collisions. Sort of, but the matter still interacts with each other. I mean, it can literally collide with each other. So you get other forces that come in, shocks and stuff, which is all electromagnetic stuff comes in. So it's those things which counter the gravitational force. There's another question over here somewhere. Yes? Sorry, can you say that a little louder? Do we know when or how electrons came about in the universe? Oh, that's a great question. So we know that at the time when this stuff was happening, that there were electrons running around as well. So it's just that they had so much energy, they were free. So So this is, so I have a little bit on this in the slides, but as we go back in time, there was even more beyond this earlier in time. We think there was a time when there was much more matter and antimatter that was around in the universe. This is such a fundamental question that I hate to answer it so fast, but I will, which is even earlier times, we know that there were a lot more electrons, and there were a lot more anti-electrons, which were particles they could annihilate with. And when we get along to this point in the universe, all of those have annihilated with each other. And so we're just left with a little bit of residual amount of electrons. So the electrons were there early on from the start in the explosion. So, but there were a lot more of them. So one little topic, which is really fundamentally very important, which I've kind of skipped over here, is that we don't understand why this matter is still here. If we want to create particles now in the universe, like if we want to create protons or neutrons or electrons, we can only do that by creating their antiparticles as well. So if we want to create an electron, we have to create an anti-electron. For some reason, when the universe was created, those were not equal. The universe created a little bit more electrons than it created anti-electrons. And so most of those annihilated with each other and disappeared, and we've got the little residual amount left over today. That is one of those questions that we cannot answer. Why? Why did the universe create a little bit of extra stuff, regular stuff as opposed to the anti-stuff? That's what we are all what we are all made of today. We can't answer that. But there was a lot more back in the early days. So. Okay, so we'll have to continue this on the forums if people have any more questions. So you guys have a very safe and happy holidays. Thanks for coming today.